I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this opportunity we have just to meet together again, Lord, and study your creation. I just pray that you be glorified as we study math, and I just pray that we have a good time this weekend that's about to start. Amen. Sooner for you than for me, probably. But yeah. So, any questions about anything in particular? All right. Let me just throw a couple problems on the board and see if we can do them. How about the integral of x squared e to the minus 3x dx? All right. All right, so Liate, log, inverse. Which should we pick here? If we trust the Liate. The u should be what? Oh, algebraic, right? So this should be our u. So this is going to be my dv. So I'm going to have uv minus integral of v du. So if dv is e to the minus 3x dx, that makes v equals to minus 1/3 e to the minus 3x, right? So I get minus 1/3 x squared e to the minus 3x plus 1/3 the integral, what's du? Worked myself into a tight spot here. Du would be 2x dx, right? So I got 1/3, I've got my e to the minus 3x, and then I've got 2x dx. Let me just clean this up a bit, since it's got a little scrunch there. Minus 1/3 x squared e to the minus 3x. I'll pull the 2/3 out front there, just for the sake of being annoying. Well, I don't know, it's not really annoying, just clean it up. And then I'm going to write x e to the minus 3x dx, because that helps me make the next step neater. So we're not done, but we're getting closer to our goal, which is to find the complete simplified integral. You see, we've reduced the power here from 2 to 1. So it seems like if we do this again, we'll be done, right? So this time, let's let this be dv2. We'll let this be u2. So u2 equals x, du2 is dx, dv2 is again e to the minus 3x dx, which makes v2 minus 1/3 e to the minus 3x. So there's my integration by parts. Let's see here. I'll write it down here. I'm supposed to do u2 v2 minus the integral of v2 du2, right? So what is that? So u2 v2 is x, well, minus 1/3 x e to the minus 3x. That's my u2 v2 term. And then minus the integral of minus 1/3 e to the minus 3x. This time du2 is just dx. Fine. Let's see here. And then I've got myself a minus minus gives me plus. I get plus 2 over, I get 3, I get 3, I get 9, and minus 1/3 e to the minus 3x, yeah? because the integral of e to the minus 3x is, again, minus 1/3 e to the minus 3x plus a constant. I'll clean it up just a bit. So we've just calculated the integral of x squared e to the minus 3x dx is, looks like there's a common e to the minus 3x everywhere, isn't there? Yeah, we can pull that out front, e to the minus 3x. And we've got like minus 1/3 x squared. I could have probably factored out a third too, but I just didn't. Minus 2/9 x. Then what's the third term there? Looks like minus 2/27. Yeah. Close parentheses plus a constant. There you go. So this time we had to integrate by parts 2 times in order to do that integral. Right. Any questions? If you ran up against like integral of x cubed e to the x, you kind of know what you'd have to do, right? To integrate by parts 3 times. But we would rejoice that it was e to the x and not e to the 3x, right? Because having a number up in here makes the arithmetic get muddy. You gotta be careful. Any questions? What if we had a definite integral? What if I asked you the integral from 0 to 1 of x squared e to the minus 3x dx? I mean, you can do integration by parts with bounds, right? But there's no need for that here. We found an antiderivative, so we can go back and use the fundamental theorem of calculus and say, okay, well, it's, let me call this whole thing without the c. I'll just call this whole thing, f of x, right? So this should be f of 1 minus f of 0. Now, f of 1 is e to the minus 3 minus 1/3 minus 2/9 plus, minus 2/27. And then minus f of 0 would be e to the 0, which is 1, minus 2/27, because x is 0. So this would be the integral from 0 to 1 of that function, whatever this is. I mean, you could clean it up a little bit, but I think that's good. I mean, I would want you to write e to the 0 as 1. That would be good. I mean, oh, fine, I'll simplify it. Let's see here. So this is e to the minus 3. You talked me into it. Make a common denominator of 27. All right. Pull a minus out front to be civilized. So with that, this becomes, what, 9 plus 6, because 2 times 3 is 6, plus 2, plus 2 over 27. What's 15, 17? All right, so 1/27. What did we just say, 17? So 17 over e to the 3rd power with a minus, plus 2. There you go. That's kind of neat. Of course, you could find a number if you had a calculator, right? You could find a decimal, but that's the exact answer, yeah. Okay, so what's integration by parts with bounds? Let me just write it down. I haven't written it down yet. I don't think. We didn't come across it last time, did we? But if we have the integral from a to b of, oh, stink. This is going to be ugly, but you'll bear with me here. So u dv dx is equal to uv evaluated from a to b minus the integral of v du dx from a to b. If you want me to write it without the x's, then I have to change the bounds to match the u or v variables. right? But let me look at an example of that. How about, so example 2, suppose we wanted to integrate x sine x dx from 0 to pi, let's say. So how this actually, I mean, I wrote what's true there, but let me show you how we actually do it in practice. It doesn't look quite that, I mean, it doesn't look like this exactly when we actually put it into practice. This is going to be my dv, this is going to be my u, right? So uv evaluated from 0 to pi minus the integral of, fine. I'm going to skip the middle step as to not belabor notation, which is not so interesting. All right, so if dv is sine x dx, what's v? It's minus cosine x, right? And if u equals x, what's dv? du, rather, is dx, right? So what we do is we do x, I had stupid minus x cosine x, I evaluate from 0 to pi, and then I add the integral from 0 to pi v du, which is cosine of x dx. So it's just like what we're doing, except you tack on bounds, and the uv term gets evaluated from, you subtract the term at the top minus the term at the bottom, just like fundamental theory calculus. Let's see here, what's that actually work out to? I keep working myself into a tight spot there. What do I got? I got minus pi cosine pi plus 0 cosine 0. And then what's the what do I do?
Is the derivative of sine cosine, not negative cosine?
But it's the integral of sine that we're doing, because to get from dv to v, we got to integrate, right?
Oh, crap.
So the question is, if you differentiate v, do you get back dv, right? Like derivative of uh-oh. Yeah, 50-50, right? Yeah. So my friend Crazy Paul, I remember. It's if I tell you enough stories, you'll understand. Like I'm taking differential equations with him. He's still asking me about the derivative of sine is minus cosine? Is it cosine? Is like, we're in differential equations, Paul. You're still asking me this. It's like, oh. Paul's very annoying. He was successfully crammed like a third of differential equations into literally 2 hours of studying. Like I taught him the first third of differential equations in about 2 hours in the library. And he made a decent grade on it too. And then he promptly forgot it. So he has sort of extreme cramming powers. Not good for your long-term, academic prognosis. But anyway, he's a good guy. Cosine, integral of cosine is sine, yeah. So plus the sine of x, fundamental theorem evaluated from 0 to pi, which of course gives us sine of pi, sine of 0. All right, so what does this integral work out to? So can we simplify that? Negative pi cosine pi can be written as what? Yeah, just pi. Okay.
Could you also do there and do that?
Yeah, this is always an option we have, right? When you have an integral with bounds, we can always find the antiderivative first and then apply the fundamental theorem of calculus, right? Or you can use that sort of theorem and do the bounds as you go. You got to be careful. With u substitution, if you don't change the bounds, you could be wrong, right? And the same thing is true here, depending on how you denote things. But anyway. Here, let's do one more. Yeah.
Is that to say that you can take, so if you have
just take the antiderivative and then plug in the bounds or no?
Yeah, I mean, that's what I did here.
Gotcha.
So,
I'm sorry.
yeah, there are flavor choices, yes. Here, let's try this one on for size. What if we wanted to integrate x over the square root of 6x plus 1?
That's a 6x, yes.
Yeah, 6, yeah. This ain't integration by parts. I let u equals 6x plus 1. So then x is equal to u minus 1 over 6, right? And dx is 1/6 du because of this. And so with that substitution, this is just straight up 1 over square root of u, my x, u minus 1 over 6, my dx, du over 6. So that's 1 over 36 u over the, 1 over 36 integral u over square root of u minus 1 over root u which is what? That's the square root of u. So I'm going to rewrite it in power notation. So that's u to the 1/2 minus u to the minus 1/2 as it happens. I'm sure there's some way to do with integration by parts, but I don't much care because if I can find a u substitution way that's clear, I'll do u substitution, you know? I mean, it's easier. Okay, so then integrate, you know? So that's 1/36. 1/2 plus 1 is what? 3/2. 3/2. You divide by 3/2, it's like multiplying by 2/3, right? So we do 2/3 u to the 3/2, and then minus 2 u to the 1/2 plus a constant. So that's actually, what's 18 times 3? 54? 1 over 54, 6x plus 1 to the 3/2 minus 1/18 square root of 6x plus 1 plus a constant. There you go. Well, that was, I mean, I did want to give you some examples that weren't integration by parts, but I wasn't planning on this one being that. That was example 3 for us, yeah. I mean, this is just kind of a generic trick. If I've got an ugly looking denominator, right? If I can make a substitution that the whole thing, I mean, if I can make a substitution that simplifies that denominator, right, in such a way that its derivative is already sort of upstairs, then that means a u substitution's in order, right? I mean, if what was in the square root was like a cubic, right, and upstairs I just had the x, then I wouldn't try this, because if I have a cubic downstairs, I need like a quadratic piece to pick up the du thing, you know? But here, we're in business. Let's look at another example. Question? No? This one sometimes throws me for a fit. Integral of the sine of the square root of x. Now, I'm right here with you guys. I haven't worked this before class, my memory is not so good that I remember what the u substitution was. I mean, the integration by parts, what I should make u here. I do remember integration by parts solves this problem from last year or whatever, but what should we try to make u here?
Square root of x.
I think, yeah, that's if we trust the slogan, the ate. So if u is equal to square root of x, what's du equal to?
1/2
Yeah, 1/2 square root of x dx, right? So this tells me that dx is 2 root x du, right? In other words, dx is what? Dx is equal to 2u du. Oh, cool. Look at it. So this is equal to the integral of sine of u, and dx was 2u du. I was saying integration by parts, but after I wrote that down and look at it for a second, I'm like, wait a minute. U substitution is a good move here. Now, it doesn't solve the problem, but what did it just do? It got us to a problem we know how to solve with integration by parts, right? See, because we know how to integrate x times sine x with integration by parts. That's the pattern here. It's u times sine u. So, all right. And tell you what, to make our life easier, let me not use u in this step. Let's use a w. W, 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 W. There. So this is really 2 times the integral of w sine of w dw, right? So now I'll let sine of w dw be my dv, I'll let w be my u, and I get 2 uv minus integral of v du. Let's see here. If dv is sine w dw, what's v equal to? Minus cosine of w this time, right? So yeah, it's that again, isn't it? Yeah, it came back. Never left us, did it? All right, so where was I? U? U equals what? I should probably actually down. It hurt me not to write it down. U equals W. Du is dw. That's the what's going on here. Integration by parts. So I've got W minus W cosine W plus the integral of cosine W dw, which is minus 2w, excuse me, cosine of w. This is very exciting. Don't listen to my yawn. Plus 2. Hey. What's the integral of cosine? Oh, sine. Yeah. At least you guys remember. All right, let's see here. Plus constant. Are we done? I mean, we're done integrating, but are we done? We're not done. We're not done until we have our answer in terms of x, right? So what's x? What's w? W is what? Square root of x, right? So this is minus 2 square root of x cosine square root of x plus 2 times the sine of the square root of x plus a constant, and there you go. That's how you do that integral. This is a mixed method one. We do a u substitution followed by integration by parts. Yeah. Oh, that was your question?
Yeah.
Wow.
I was wondering, like, that common to have to do a U sub to get to integration by parts?
In the problems towards the end of the section, yes. But anything's, I mean, you know, all things are possible, right?
Is this what the
Is lit-
quiz is?
What's that?
Is this what the quiz is? What about all this?
I mean, I want you guys to learn how to use these techniques of integration to solve problems that are like problems that I did in class and or your homework. But to describe the entire scope of the method is like way, way more technical than what I ask of you. There are methods, actually. There's like mathematics that will tell you, given an expression, when it is possible or not to find the integral in terms of closed form elementary methods. There's something called Risch's algorithm, which actually gives an answer to this through like sophisticated mathematics. For example, this thing, no matter how many techniques of integration we throw at it, we're never going to find an elementary derivative for this thing in terms of elementary functions. It's outside our scope. And yet, this you could have done last semester. So it's really hard to describe when it's not possible to find a nice formula. Yeah.
Define elementary methods.
Integration by parts, partial fractions, trig substitution, things we're learning.
I mean, like what calculus, like what level of math would you get to where you would learn the non-knowledge?
You guys will know all of the major methods by the end of about the next week. There's really not much else out there. Yeah.
I had a professor once tell me that most, a lot of functions are actually the majority are not integrable, and the ones that are, like,
See, I think this is dangerous to say because the fundamental theorem of calculus says that if f is continuous, then the integral of f, that antiderivative area function exists, and that the integral from a to b of f of x dx is f of b minus f of a, right? That's just if f of x is continuous. So what do you mean by integrable is the question, right? See, because some people would use the term integrable to mean that you can integrate it. You can integrate it. It's just that there's not a nice formula for the antiderivative.
and wait, you said we're going to learn most of them by like the end of the week. We're going to do like the trapezoidal stuff and all the shells and all that? Or?
Those aren't nice. Those are approximations. Those, no, I don't. But, I mean, I will follow the schedule I made. I make it so that I don't have to remember these things. Let's see here. So, yeah,
Would we ever have to do use of after the integration by parts?
all things are possible. Yes.
What you did over there with the u equals 6x plus 1, and do you just do that to do u substitution a little differently?
Yeah, I did this because there's this x sitting up here. So,
You get the same thing.
Find the value for that x.
I did algebra.
Oh, u minus 1 over 6.
If you do like the regular use, so you get the same thing.
I solved for x this equation. I don't know. Subtract 1, divide by 6, put x on the other side.
Oh, I see. Got it. Thank you.
Just algebra. Hmm. Here's something scary. Integral, I'm not sure, I would answer your question, Joshua, is it? I don't know what I'm not sure I understand your question yet. Let it, you think about it, and you can ask me after class if it comes to something more rigid. So sine of x dx. So this allegedly is equal to, so he claims, minus x to the n cosine of x plus n integral of x to the n minus 1 cosine of x dx. Can we show that this is true with integration by parts? let's see if we can do it. So if we let this be dv, right? And if we let this be u, then uv minus the integral of v du is what? It's x to the n. The integral of sine x, as we've discussed ad nauseum today, minus cosine of x. And then plus the integral of cosine of x, what's du? I still need my du is what? My du is n, x to the n minus 1 dx, right? And so, yup, minus x to the n cosine of x plus n integral of x to the n minus 1 cosine of x dx. There you go. That's a formula for the integral of x to the n sine x. So the problem just asks you to show that that formula is true. Yeah.
What is the n out front?
It's a number. I pulled it out.
Oh, okay.
Nothing too fancy here. I mean, we actually did this for n equals 1 right over here. Well, with the w notation, but you notice like this is n equals 1 with w replacing x. See, it's minus x cosine. That's the minus x cosine term, then plus the integral of cosine. But if n equals 1, x to the 1 minus 1 is x to the 0. It's cosine. Yeah. So, okay. Well, that was not as I was hoping for something more sort of annoying. That one wasn't that annoying at all. Very disappointing. You guys seem like you're getting comfortable. Let's move on to the next topic. So actually, the longer I stay in integration by parts doing examples, the more disturbing it will become to you. Because you'll start to realize that there's so many different possibilities to deal with, right? So how do you prepare yourself for those things? You practice. You know I was going to say it. I mean, like you find a life coach and you repeat 10 times each morning. I can do math. 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 See, I could be a life coach. I could be a math life coach. Why don't we have math psychology? Right? We should have math psychology. We have like math life coaches every morning. They call you up and they go, "You're good enough. You're smart enough. Doggone it, people like you." Something like that. So section 8.3 is one of my absolute favorite topics. And this is really more of a grab bag of examples than it is a method per se. So this is not like integration by parts in the sense that here I'm really trying to share with you a standard list of examples and how we deal with them. For the most part, the techniques which are needed to do these are trig identities, U substitution, and just a sort of a grab bag of tricks. Let me start out with powers of sine. First of all, integral of sine x dx, I think we've actually already talked about this today, is negative cosine. Very good. What about sine squared? You do this half angle thing, right? 1/2, 1 minus the cosine of 2x. It's a little bit annoying, but you remember this identity. I mean, if you don't remember this identity, you're up a creek, but oh well. Minus 1/4 sine of, I'm sorry, is that insensitive given Texas? That wasn't a creek, that was a hurricane. Come on, guys, pay attention. Let's see here. X over 2 I'm surprised there aren't students like saying, I'm going not to be at your class because we're taking a trip to Texas to help. That must be in the works. Like soon, students will be absent from my classes because they're cleaning up stuff in Texas. This will happen. Aha, see? They won't be back in time for class next week, guaranteed. Let's see here. I mean, I'm fine with that, but let's see here. Where are we? Oh, plus a constant, right? There you go. All right. How about sine cubed?
Are
we supposed to know these from calculus?
Maybe, maybe not. I'm going over them here. Yeah. Well, probably not if you follow this book. Yeah. I personally would teach them in Calc 1. But not everyone has the will of fire. Let's see here. So, integral sine squared x sine of x dx. That's really not the technical meaning of will of fire, but somehow it works. Anyway. Yep. So to integrate sine cubed, we break off a sine squared and convert it to cosine squared. In so doing, a u substitution appears. As if from nowhere, we see u equals cosine x es bueno. So if u is cosine x du minus sine x dx, and so 1 minus u squared minus du, with this u equals cosine substitution, yep,
Wouldn't you be 1 minus cosine squared x?
because u equals cosine works. I don't want to make u equal 1 minus cosine squared, because then when I differentiate it, that would give me like minus 2 cosine times minus sine dx, but I don't have a minus 2 cosine sine dx to make a substitution. What I have here is a sine x dx, which is that. So, I mean, you can always try whatever for a u substitution, but it's not, you know, we have to change the measure and the integrand, and we have to do both at once in concert in such a way that it lands us on something that we can actually hack, and that's what this is. So this is the integral of u squared minus 1 du, also known as 1/3 u cubed minus u plus a constant, and there you go, 1/3 cosine cubed x minus cosine of x plus a constant. That is the integral of sine cubed. It's actually not that hard. Actually, instead of doing sine to the fifth, let me do cosine to the fifth. How would that be different? Yeah.
You split up 2 of x, or square of x, and you simplify those out as 1 plus cos of 2x over 2.
Oh, no, no, no.
Or,
Oh, no, 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 no. I mean,
you can pull it out.
you could do that. But no. What you want to do here is like 1 minus sine squared theta, x rather, quantity squared. That's what these guys are, right? So the game, I mean, basically the idea is if you have an odd power of sine or cosine, you can split off an even factor of it, convert it to the opposite thing, either sine or cosine, and then you'll have like one leftover sine or cosine, you can make the du, and so we can make a u substitution for odd powers just like this, yeah.
I'm like confused, as like I thought it was 1 plus cos of 2x over 2. For, like,
That is true, but we don't need to do that here.
Okay.
Because if you did that, well, you can try that, but it won't, I don't think you'll get far. Because after you do that, you've still got a leftover cosine. Then you got like cosine 2x times plus 1 divided by 2, and then another cosine 2x plus 1 divided by 2. You got to multiply those together, and there's still another cosine that you're multiplying those by. Then you have to integrate. But see, the reason to do this is that when I make u equals sine x, that this becomes the integral 1 minus u squared, quantity squared, du.
So you're using the other, the sine cos plus cos 2x is 1. So you have to use both identities.
For odd powers, we can basically just work off the Pythagorean identity. For even powers, we need the half angle stuff, yeah. Yeah.
That du should be cosine of x, right?
Oh, yes, thank you. I'm guessing that was both of your questions, no?
Yes.
Okay. Much appreciated. And then how do you do this integral? Well, you FOIL it out, right? Did I say FOIL? I feel dirty. You distribute using algebra. We get 1 minus 2u squared plus u to the 4th, and then you can integrate, right? U minus 2/3 u cubed plus 1/5 u to the 5th plus a constant. It's not done until we put it in terms of x. So we got like sine x minus 2/3 sine cubed x plus 1/5 sine to the 5th of x plus a constant. If you understand 3 and you understand 5, you should just as well be able to do 17. But you should also know that someone should pay you money to do that, because it's a pain, right? I mean, this step gets worse as we get larger, right? Yeah. Also, integral of sine to the 4th. It's not fun. See, because integral of sine to the 4th, what does that mean? We got to square this thing, right? What happens when you square that? You get 1/4 integral of 1 minus 2 cosine 2 theta plus cosine squared 2 theta, right? Now the first two terms are harmless. We can integrate those. Easy peasy. But the last one, well, we got to use the half angle identity again. So this gives me theta over 4 minus 2 over 4 times 2 sine of 2 theta, and then plus 1/8 the integral of 1 plus the cosine of 4 theta d theta. So this guy right here, I expanded using the half angle identity. See, the 2 theta times 2 becomes 4 theta, and it pops out that 1 and another factor of 2, the trig identity. Now we can integrate that, and we get ourselves a theta over 4 minus 1/4 sine 2 theta plus theta over 8 plus 1 over 32, the sine of 4 theta plus a constant. So if some professor asked you to integrate sine to the 6th, you should just punch them in the face, pretty much. I mean, it's just not nice, you know?
So you're not going to ask us to integrate sine to the 6th?
I might. I would put that test down and then I would just leave the room. Like, you just walk away. Oh, you see me the next day? Oh no, oh no. All right, so first order of business, I feel like, is how do you integrate any power of sine or cosine? It's a pain, but you see you can integrate any power of sine or cosine using these methods. There's also iterative formulas, like reduction formulas. Maybe I'll do those next time. I don't want to try to squeeze them in right now. But there's also like a way of linking the third integral with the second integral of sine and the third integral with the second integral of cosine. There's like recursive formulas that you can also use. Other professors prefer those. These methods serve me well. I don't have to memorize some recursion formula, but whatever. So what's the next order of business? How about integral of tangent? or tangent squared, or tangent cubed? What about integral of secant? Or secant squared? Oh, secant squared. Hey, we like that one. Right? So let's let's pick on secant. Weirdly enough, this one's the easiest. Integral of secant squared theta d theta is? Yeah, tangent theta plus a constant. That one's not bad. Something unpleasant happens here. Secant theta d theta. So I'm going to show you a trick, which is nice. You let u equal to secant theta plus tangent theta. I mean, obviously you should make u equal secant theta plus tangent theta, right? I mean, just look at this integrand. It's clear, right? I'm joking. But just follow me. So du d theta is what? Derivative of secant. Secant tangent, right? What's the derivative of tangent? Secant squared. Look at that. Factor out of secant, we get du d theta is secant theta times tangent theta plus secant theta, right? Aha! This is u. So what we have is that du over u is equal to secant theta d theta. Hooray. So this is the integral of du over u. This is a rather different kind of u substitution than you're used to, right? But it is just a u substitution. Natural log the absolute value of u plus a constant. And there you have it. That's the integral of secant. Natural log the absolute value of secant theta plus tangent theta plus a constant. Now, you might be like, Professor, that seemed kind of like hard and stuff. You're not actually going to expect us to know that one. No, actually, I do expect you to know this one. You either need to remember how to derive it, or you need to remember how to derive this, or just to remember this result as well. If I want you to derive it like I just did, I would say make a u equals secant plus tangent substitution to show that this is, to derive the integral of secant. So I might ask you to like redo that example sometime. I don't know what example number I'm on. It doesn't matter. Let's go on here. How about, yep.
Wait, so how can you just add in like that?
This?
Yeah.
This is a thought. I mean, that's the starting point. I just said, let u be that. If you look in Larson, he's got some little calculation that kind of motivates it, but not really. If you want the truth for me, you wonder where I first thought of that. I didn't. My wife told me it. She took calculus in Hong Kong in high school, where she learned this and a host of other things that I don't teach you guys. So.
Doesn't you have to be in like when?
No.
Is there any other way to derive it?
It's just usually, if you write u equals some random function of things that are like the problem but not the problem itself, it's not helpful. But here, it happens to be rather helpful. Now, suppose you want me to derive it. You want me to derive it. Fine. I hear you. This is d theta over cosine theta, which we can write as the integral of cosine theta d theta over cosine squared theta. Hey, that's the integral of cosine theta d theta over 1 minus sine squared theta, which, by the way, is equal to the integral of 1/2 1 over, I think, 1 plus sine theta minus 1 over 1 minus sine theta, or something like that, up to a sine. Pun intended. Cosine theta d theta. And then you could integrate that using u substitution. What I'm doing is a combination of substitution and partial fractions. But to me, I don't tell you this right now because it's too complicated. And even when you know these methods, it's still too complicated. This is still a better way. So like, there are ways of deriving this using other things, but like this is the most efficient way I can explain to you why the integral of secant theta is log of secant plus tangent without just saying, this is true, differentiate it and see for yourself, right? If you differentiate this, you get back to that. I don't think that's immediately obvious either, but it's apparently true. So it's just it's a tough integral. I mean, I can't sugarcoat it. It is a tough integral. This one, on the other hand, is actually not that bad. How would you integrate tangent squared? Yeah?
You take
No, that
2x plus 2 of x, and then I feel like you can substitute, so to get tangent, sine over cosine.
you guys got to be lazier. This is something we know right here, right? It's fine. We should try things. They may or may not be helpful. But since the weekend has to start, I'm going to give it a little nudge. So this is super useful, but we also know that secant squared plus secant squared theta is equal to what? Tangent squared theta plus 1, yeah? So tangent squared theta is the integral of secant squared theta minus 1. So this is just tangent theta minus theta plus a constant. Game over. It's weird to me that the integral of like the first power of secant is much more difficult than the second power. By the way, integral of secant cubed, like the first time I asked my wife, it took her like a solid 5 minutes to figure it out. She was walking without paper, she'll tell you, like, because she takes offense, like me saying it took her 5 minutes, but, you know. I think Ginny is better at integration than most math professors, so it's, anyway. I digress. So anyway, you guys have a good weekend. If you get stuck on your homework and you need a help, just email me. It's all good. We were supposed to end at 4:05, right? I'm sorry.